When we investigate the behavior of solution, we find that solutions of some substances, the non-electrolytes, will not conduct an electric current, while solutions of others, the electrolytes, will. When the bulb lights, we know that the circuit is complete and that electricity is flowing through the solution. Michael Faraday, an English chemist and physicist of the 19th century, performed many experiments concerning the electrical conductivity of solutions. He theorized that a current flowed through a solution because molecules of the solute had been split by the electric potential into charged particles he called ions. Svante Arrhenius, a Swedish chemist, in 1887 put forward his theory of electrolytic dissociation. Arrhenius believed an electric current was not necessary for the formation of ions. Arrhenius's theory, though it has since been modified, provides the foundation for our present understanding of ions and ionization. Pure water will not appreciably conduct electricity. But if we dissolve hydrogen chloride gas in the water, a current will flow. Watch the bulb light. Because the current is flowing through the solution, we know that ions must be present. Molecules of the gas, hydrogen chloride, each contain one atom of hydrogen and one of chlorine. A hydrogen atom consists of one proton as a nucleus and one orbiting electron. Actually, if we think of the proton as the size of a pinhead, the electron would be about 40 feet away. A chlorine atom has 17 protons in its nucleus and 17 electrons in orbit. There are 7 electrons in the outermost ring, which can hold 8. When the hydrogen atom and the chlorine atom form the hydrogen chloride molecule, they combine in such a way that the hydrogen and chlorine atoms share a pair of electrons. Such a compound is called covalent. We might also represent the hydrogen chloride molecule this way, three-dimensionally. Water is a covalent compound too. Here is a three-dimensional representation of the water molecule, with its 2 hydrogen atoms and 1 oxygen atom. The hydrogen end of the molecule tends to be positive, and the oxygen end tends to be negative. Such a molecule with 2 poles is said to be a dipole, or a polar molecule. Polarity is caused by non-uniform electron distribution. The hydrogen chloride molecule is polar too. The hydrogen end is positive, and the chlorine end negative. When hydrogen chloride is dissolved in water, the attraction of the polar water molecules is strong enough to break the covalent bonds of the polar hydrogen chloride molecules. In a dilute solution, about 95% of the hydrogen chloride molecules are broken up in this way. The proton nucleus of the hydrogen atom separates from the chlorine atom, leaving behind both shared electrons. Changing the number of electrons in the outer shell of an atom also changes its properties. Therefore, the properties of the hydrogen and chlorine atoms have changed, and we can call them ions. Negative ions are larger than the parent atom. Positive ions are smaller. The hydrogen atom's single electron has now completed the outer electron shell of the chlorine atom. The chlorine atom has 17 positively charged protons in its nucleus. When it has 17 negatively charged electrons, it is electrically balanced. But now, with the additional single electron that once was part of the hydrogen atom, the chlorine is electrically unbalanced. It has a charge of -1 and is called the chloride ion. The hydrogen atom consists of 1 positively charged proton as a nucleus. When it has its 1 electron, the atom is electrically balanced. But with the negative electron gone, the hydrogen is left electrically unbalanced with a positive charge of 1. It is a proton now, or a hydrogen ion. Whenever neutral atoms gain or lose electrons, ionization has taken place, and ions are formed. The number of positive or negative charges on the ion is its valence. Hydrogen chloride in water solution is called hydrochloric acid. All acids ionize and are electrolytes. We can express the ionization of hydrogen chloride this way. One molecule of hydrogen chloride yields a hydrogen ion with a single positive charge and a chloride ion with a single negative charge. The hydrogen ion is a proton. However, hydrogen ions actually do not exist free in water solution, but are hydrated, attached to a water molecule. Covalent compounds, such as hydrogen chloride, are not ionized in every solvent. Benzene does not conduct electricity. When hydrogen chloride is added to it, electricity still does not flow. Benzene molecules are not polar, and so they cannot exert the attractive force necessary to break the covalent bonds of the hydrogen chloride molecule. No reaction occurs between the benzene and the hydrogen chloride. No ions are formed, no current flows. We've seen, as in the case of the hydrogen chloride molecule, that ionization is the process whereby a neutral atom gains or loses electrons. We can expand that definition. When hydrogen sulfate is added to water, the current flows, so we know that ions are now present. The solution is called sulfuric acid. We can represent what is happening this way. Here is a hydrogen sulfate molecule. The two hydrogen atoms on the left are each sharing a pair of electrons with an atom of oxygen. The ionization of H2SO4 in water takes place in two steps. The one atom of sulfur and four atoms of oxygen have separated as a unit called a radical. The radical takes with it the single electron from each of the hydrogen atoms. The hydrogen atoms have become ions, or protons, each with a single positive charge. The one atom of sulfur and four of oxygen, called the sulfate radical, now have become an ion with a negative charge of -2. This charge comes from the two electrons gained from the two hydrogen atoms. So now we can say that ionization is the process whereby a neutral atom, or group of atoms, gains or loses electrons. Notice that when H2SO4 ionizes, 3 particles are formed, 2 hydrogen ions and 1 sulfate ion. We have seen that acids are electrolytes. Let's see if solutions of bases conduct electricity. Sodium hydroxide is a base. Its water solution does conduct electricity, therefore we know that ions are present. We can represent the ions of sodium hydroxide in water this way. The sodium ion has a valence of +1, and the hydroxide ion, which is a radical, has a valence of -1. All bases ionize in water and are electrolytes. What about salts? When we test dry sodium chloride for conductivity, it is clear that no current flows. Apparently, there are no ions. Now, while we keep a potential between the electrodes, let's heat the sodium chloride to its melting point. Several minutes later, when the temperature reaches about 800 degrees centigrade, the salt will begin to liquefy at the bottom of the crucible. Watch the bulb. Now it is clear that current is flowing through the molten salt, so ions must now be present. Actually, Ions were present in the sodium chloride crystals from the start. Solid sodium chloride is 100% ionized. Sodium chloride is called an electrovalent compound. When it is formed, there is no sharing of electrons. Instead, the single electron in the outer shell of the sodium atom is transferred to the outer shell of the chlorine atom. So, ionization has taken place. The sodium ion has a charge of +1, and the chloride ion a charge of -1. This relationship is called electrovalence. Raising sodium chloride to its melting point gives the ions mobility. This same mobility of ions is achieved by dissolving sodium chloride crystals in water. The separation of ions from the crystals of electrovalent compounds during the solution process is called electrolytic dissociation. In general, most salts are in the ionic form. As the crystals of sodium chloride dissolve, sodium and chloride ions are surrounded by the polar water molecules. The negative oxygen end of the water dipole is turned toward the positive sodium ion, and the positive hydrogen end of the water dipole is turned toward the negative chloride ion. When there is an electric potential between electrodes in the solution, the positive ions tend to move toward the negative pole, picking up electrons there, and the negative ions move toward the positive pole, releasing electrons there. This action is fundamental to the flow of electricity in a solution. It also explains the process of electrolysis, in which a compound, either the solute or solvent, is separated into simpler substances by an electric current. Pure water ionizes slightly, even though it does not appreciably conduct an electric current. Only about 1 water molecule out of every 10 million will ionize. The process probably occurs this way. A hydrogen bond forms between 2 water molecules. Under just the right conditions, this bond might be stronger than the normal covalent bond of one of the molecules, and so ionization takes place. The result is a positively charged hydrated proton, which we call the hydronium ion, and a hydroxide ion with a single negative charge. These few ions have an important bearing in the electrolysis of water and in hydrolysis. Ions affect the freezing and boiling points of solutions. Here is a 4-molal aqueous solution of an electrolyte, calcium chloride. In the test tube is a 4-molal solution of a non-electrolyte, sugar. Solutions of non-volatile substances have higher boiling points than pure water. But watch as we heat the 2 solutions. In a few minutes, the sugar solution in the test tube has begun to boil before the salt solution in the beaker. Salt raises the boiling point of water more than sugar does. Careful experiments show that a 1-molal solution of sugar raises the boiling point of water 52/100ths of a degree centigrade. A 1-molal solution of calcium chloride raises the boiling point 1 46/100ths degrees centigrade. Calcium chloride raises the boiling point about 3 times as much as sugar does. The freezing point of water is similarly affected. The freezing point of pure water is 0 degrees centigrade. A molal sugar solution lowers it 1 86/100ths degrees centigrade. A molal solution of calcium chloride lowers it 5 21/100ths degrees centigrade. Again, the effect of the calcium chloride is almost 3 times that of the sugar. The abnormal effect on freezing and boiling points by electrolytes can be explained by ionization. All molal solutions contain the same number of molecules. When solutions of sugar and calcium chloride are prepared, For each molecule of sugar, there is only one particle in solution. But for each so-called molecule of calcium chloride, 3 particles are actually present. Since the boiling point and freezing point of a solution depend on the number of particles of solute present, the effect of calcium chloride should be 3 times the effect of the sugar. It is actually a little less than that because of interionic attraction, which causes some of the calcium and chloride ions to clump together. While our understanding of ionization arose mainly from a study of electrolytes, the theory of ionization has many applications in science. Certain vacuum tubes, called thyratrons, contain a rarefied gas, such as argon, neon, or mercury vapor. When streams of electrons emitted from the glowing filament acquire the necessary speed and energy, a point called the critical grid voltage is reached. The gas in the tube suddenly ionizes, and a large current flows. This trigger characteristic of thyratron tubes makes them useful in switching and relay applications. Thyratrons are especially useful in lighting controls. Geiger counters and other types of radiation counting instruments also depend on ionization for their operation. Radiation ionizes molecules of a gas within the Geiger-Müller tube. Each time molecules of the gas ionize, energy is conducted in small bursts between 2 electrodes in the tube at high voltage. These bursts of energy are mechanically counted, giving us a measure of the radiation being emitted. Another application of ionization can be found in the process of electroplating. In this process, ions of a metal whose salt is in solution are deposited as atoms on an object used as a cathode during electrolysis. This electronics equipment is being cadmium plated. The principles of ionization have been put to many practical uses. But more important, our understanding of ions and electrolytic dissociation is basic to our growing knowledge in the field of chemistry.